Hello and welcome to the video version of Technology in Space, where we talk about the science, technology, history, and business of space exploration and commercialization. I'm Chris Alvarez, and thank you for watching.
This is part one of two parts.
I'm speaking with James Miller, who is an expert in spacecraft, in unmanned spacecraft navigation. You wrote a book on the topic, and I've done multiple interviews with you, which people can find on the channel. And so we're just talking again about the stuff you've been through and the work you've done. And thank you again for speaking with me.
Thank you.
So
I like talking about myself.
it's fun stuff. So first, actually, when we finished off last time, you mentioned a few things you wanted to talk about from your notes. And I think you mentioned some things from Mariner, the purple plague, scan platform unlatch, and sun shutter problem.
Paper. Yeah. I thought it was just this. I thought it would be an interesting. The further back I go, I think the more interesting it would be. And I go back to. I started working in 1961, but I started working on the summers in 1958. So I was working at Westinghouse when the Navy took our submarine and sent it to the North Pole under the ice cap.
Oh, okay.
But it was the first couple of submarines that we made, Westinghouse made, had two screws on them to propel them, and the attack submarines, the ballistic missile submarines, the Polaris missile submarines, they had one screw, so they didn't want to take any of those under the North Pole, because if they went too high and bumped the screw on the ice, they could lose propulsion. This is very dangerous because they're flying underneath between the bottom of the ocean and the bottom of the ice cap. It's a few hundred feet. So they managed to get this thing all the way to the North Pole, and then you can find places where the ice is melted. You can punch up and surface. But anyhow, that happened. That was a big deal, and I'm sitting at my desk, and it was made of national news, But anyhow, so I've sort of without worrying about whether or not I'm really contributing anything really wonderful, I've always been attracted to going to working for places where something is going on. And this is not a good idea if you want to make money, or you want to be happy in your life, because when new things are being developed, there's a lot of tension and people are fighting with each other a lot. And so I kind of developed a thick skin, so it didn't bother me. But it really does bother you anyway. Anyhow, I was telling earlier that I've worked for 5 companies, and one of them was Westinghouse Electric, which was a major. It was one of the major, what you'd call high-tech companies. They did washing machines and things like that, and refrigerator is what they're famous for. Their Betty Furnace and the refrigerator, but they also did some advanced work on military systems. They built the first jet engine in the United States.
Oh wow!
And they also built a power plant for the first nuclear submarine, and also for the first commercial power plant. And that was all in where I was working. And then I went to work for Lockheed Martin, and it was Martin Marietta at the time. Lockheed was out in California, and they did a Seamaster airplane, a gigantic seaplane, jet powered, and they built bombers during World War II, and I worked in the building where they used to build bombers, and then I got a job at Jet Propulsion Lab, and they're on the news all the time. And I was out there, and then I went to work for a small company, and then they are out of the news altogether. And I kind of decided I like working at JPL because when things are happening, there's always problems and that come up that need really fast answers. And you have to kind of have, be prepared for this to some extent. So I always like being around because I like doing that. I'm sort of trying to give a little background because as a result of working for all these different companies, now that I'm retired for 10 years, I look back and I really don't have an outstanding favorite. And on the other hand, I don't dislike any of them. I don't. One of the, they're all the same to me.
Mhm.
So sometimes I'll say good things and bad things about the places that I've worked because it's all one thing to me.
Mhm.
If I had only worked for people who have only worked for one company all their life, for like 50 years and never worked anywhere else, they have a very narrow view of the outside world. In fact, they don't have any view of it. And they don't understand that a lot of what goes on is common. It's everywhere.
Mhm.
Like I was telling you about punching a time clock, and when I went to work at Lockheed Martin, punching a time clock was something that I really hated because I like to come in when I felt like it and go home when I felt like it. And I do a lot of work at home. I give them 40 hours a week.
Mhm.
If I work more than 40, then that's mine. Whatever it is I did, that's mine.
Yeah.
However, if there's some kind of an emergency, which does happen a lot, then you just work until the problem is solved, and you don't count that time. You're never going to get paid for it, and it just disrupts your whole your life schedule, so to speak. So I could spend 2 or 3 days maybe working around the clock, and then when it's done, I forget about it. One guy kept track of all his hours that he was putting in, and he decided to take a month's vacation to make up for all of the hours. I could have done that too, but then they fired him because higher management found out about it.
He took a vacation on his own time.
He just took a vacation without permission.
Yeah.
You owe me the time, I'm going. But I knew all the tricks to avoid getting fired. I'll tell you some more. When I started working, you have to fill out a time card. It's a little card, like an IBM card.
At Lockheed or Martin?
All the companies, yeah. Westinghouse too. And what happens is you get charge numbers. This is more so at JPL and also at Lockheed or at Martin Company. But anyhow, so you have 4 or 5 charge numbers that because you get different things you're working on. And so what you do is you fill it out in pencil, and then your supervisor looks at it and he figures out where the money is, and he puts down how many hours you worked on a different chart, and fixes it up so that it totals out all correctly.
Mhm.
And every company's doing the same thing. Everybody, you fill out your time card and pencil. So I never pay much attention to it. I put some numbers down and hand it to them, and I'd make a guess as to how many hours I worked. And it usually wasn't. When I'm working on one project, I'm usually thinking about another one.
Mm.
How do you? So anyhow, the lawyers got involved about 10 years ago or 20 years ago, and they said, okay, no more pencil time cards, or you have to actually account for every hour you work, just like a lawyer.
Mm. Yeah.
When you fill out your time card. Well, I couldn't take this seriously, so I came up with a strategy. I said, okay, here's the deal. I'm only going to work on one project, but I'll spend some time doing whatever you want. But I'm only going to put one number on the time card.
I see.
It'll be 40. I put that number down and put 40 beside it. And so I worked on big projects like Viking and Galileo, and so there wasn't any problem. Well, in between, I started working on smaller projects, but I still kept the strategy of you only have one number. And the reason for that was that I would make sure that the guy who was responsible for that one number was satisfied with what I was doing. And also, I was satisfied that he wasn't keeping track of how much time I was spending on anything, only what I was doing. Okay? So then I could do whatever I want, essentially. The problem with having two, I knew a guy who was a very highly thought of person at JPL, and I went to school with him, actually. He's one of the few people actually I remember from when I went to college. He designed the first star tracker. It was a electronic star tracker on Mariner 6. He put it on there. He designed it. He was only 25 or 26 years old. He's designing this thing. It's a photo multiplier too. And a lot of guys are doing this. I can't. He told me one time, he said, I can't believe I'm only 25 years old. I just got here and I'm designing. I'm responsible for the star tracker. Well, nowadays, you'd have to be 100 years old to be responsible for anything. But so anyhow, he got in trouble late in his career, and I heard they fired him. But what he did was he was taking money from one contract but working on another for the guy, and he was putting charges down and not putting the correct hours down. He thought that the one job was kind of stupid, so I've charged them half time, but then I'll do all my work on the other thing. Well, the two guys that he's working for, they got together and they figured this out, and he got in trouble. Really got in trouble. I could never get in trouble because I only had one.
Right.
Against his, you don't never allow a witness in the room if you're going to do anything that's a little shady.
Yeah, I'd say so.
I'm speaking with James Miller, author of Planetary Spacecraft Navigation. You can find more information about the book on the Springer website. If you like this episode of Technology in Space so far, please subscribe and hit the like button. If you'd like more books and information on space history or the science, technology, and business of space, check out my YouTube channel, Spacewalks Money Talks, my podcast, Technology in Space, and my website, technologyandspace.com. If you're looking for military history and general history, including true crime, please check out my YouTube channel, War Scholar, my podcast, Military History Inside Out, and my webpage, warscholar.org or militaryhistorypodcast.com. If you're looking for fiction, including sci-fi, horror, fantasy, mysteries, thrillers, film history, gaming, and more, please check out my YouTube channel, Chris Alvarez Full Contact Nerd, my podcast, Full Contact Nerd Interviews, and my webpage, chrisalvarez.com or fullcontactnerd.com. Now back to the video.
Okay, well, that kind of, I thought a little bit of, that brings up another point. I'm trying to make a point here.
Sure.
And that is that, when I worked for Westinghouse, we were responsible for the safety of the nuclear reactor. And at that time, they were regarded as 100% safe. And there's nobody could conceive of anything bad that could happen in terms of the reactor blowing up or melting down or anything like that. Because we had our safety systems really well designed, so they didn't take the work too seriously. But the people that I work with took it very seriously, and I always get mad when I hear the media, criticizing the companies, and the people in the companies, like at Westinghouse, never get to defend themselves. I know from working with these guys that they since human life was involved, there's absolutely no question, but that they would stand up to any company, president or anybody, and not do something if it was dangerous in any way, shape, or form. In other words, the safety was paramount, and so I never questioned that. That was safety. Well, now you go to another company like JPL, and there's no human life on any. Oh, there's human life on a submarine, and there's 125 guys on there. I remember going into work one morning when the Thresher had gone down to the bottom of the ocean and killed all 125 crew members. And this was, everybody, you could hear a pin drop. There wasn't any noise at all in there. It was the strangest thing. It really affected people to lose that many people.
Mm.
JPL, you only lose money. Spacecraft cost money. You know, if you lose one, okay, let's go spend money for another one.
Mm.
JPL had, in order to have ethics, you have to have something to be ethical about. At Westinghouse, we just threw the money at the problem. We don't care about money. It was we had to, you know, make sure everything was done right. Well, if you don't have human life on there, then it's how much does it cost? And so I always took it very seriously, because $100 million is a lot of money. That's like 100 people. That's their life earnings. I could blow that in with one bad mistake. Mm-hmm. I regarded the money aspect as like human life. Well, I just made that transfer. You know, it's money. It's dead people. It's the same to me. But the culture is more inclined to be a little less concerned about making mistakes if you know that it's just going to cost $1 billion, but it's for 100 million. 100 million is kind of the threshold that gets my attention. Any less than that, I don't care. And so you tend to be a little more careless about being careful. So yeah, I have these two opposite cultures. One is human life related, and one is money related. So the ethic, yeah, I was always regarded as a big spender at JPL. I'm used to spending money. Those guys, okay, you got the point.
Yeah, it's
the overall conflict that went through my entire life was how much do you have to be careful about wasting money?
Yeah.
I'm responsible for many forest trees being chopped down. I mean, making computer runs. I could go in there and change the computer program so that it doesn't print out so much. See? But then if I change it, I could make a mistake changing it. A lot of times I had to find something that was buried deep in the code. So if the program ran for an hour, if I printed out everything it did, it would generate a million pages. I mean, I don't know. I never tried it, but it would fill a room with paper. Mm-hmm. So to see what was going on, I would put little prints. I would isolate where I thought the problem was. I turn on a printer, and have it print for a second, and then turn off, and then finish, and then it runs to the end. But during that second, I'd get a couple inches of paper.
Yeah.
So if I kept changing that print statement, or when I isolated to the section of where the problem was, and I couldn't figure out what was going on, I would keep making different kinds of runs to try to highlight it or something. But I didn't want to change that print statement and move it around because I'm afraid I'd make some other error. I remember one Sunday I was working on Viking, and I had an error like that. And there's a dumpster that was empty. I filled it up with paper. About 4 hours. And the people who were running the computers, they were getting mad at me because they see what I'm doing. I'd pick up like a couple inch of papers. I'd thumb through it and look at it for about a second or two. And I said, oh, that's not right. Let me try this. And I'd throw it in the dumpster. But other people would, when they had memos, have a memo, they'd, you could write on the back, so they save all their paper, and make sure that they didn't waste it. And I kept telling the guy, I said, do you know how much that much paper costs? Do you know how much it costs to have you sit here and move that paper around? It costs 10 times what you save by doing that.
Yeah. That's funny. Let's talk about Mariner then. Those points you brought up. I'm anxious to hear. You said the purple plague. That was the first thing.
Well, okay. There's another thing I mentioned earlier about Bill Melbourne. Hmm. Do you mind if you talk about that first, just for?
Sure.
Okay, and then we'll go to that because that's I'm sort of prepared for this. Okay. Bill Melbourne was a section manager at JPL. I didn't work for him. I hardly knew him. However, when I went to this luncheon, I would see him there a lot, and I talked to him, and I got to know him a little bit.
Mhm.
He had about 100 engineers working for him, but he's probably I think he's the most highly respected engineer at JPL. And he was responsible for the orbit determination in the early days when they were first doing it.
Mhm.
And he was a student of Feynman, Richard Feynman. I didn't even, I asked him, oh yeah, okay. But he passed away recently. And so at this luncheon that I just went to, we were talking about some of the papers he had written. There's one, this is an article from Scientific American that he did in 1976. And there was another paper he had done for Scientific American. And these papers were really good. You read them, and I mean, what he did is explained all of the aspects of navigation.
Hmm.
And it's rare you find anybody that you can give, you can see things that you work with and you become aware of. This is true at Westinghouse, it's true at JPL, and it's also true at Martin. You become aware of how things are done, but you always wonder, who was the first guy that did this? Whose idea was this originally? I can never figure out who it was. And when I'm writing a paper, I want to reference people, I don't know who to reference because nobody really, the guy who did the original work immediately gets forgotten. That's kind of the way it works. Well, Bill Melbourne, if they go into management, they've never done anything that's for the first time. But Bill Melbourne was an exception. He had done some things that were really first that he understood, and he rose up pretty high in the management, and he never lost this desire, I guess, to. Okay, so anyhow, he wrote this paper on the Viking mission, and I had been on the Viking navigation team for 5 years, and we had a meeting once a month where we got together with the Langley Research Center and Lockheed Martin and JPL. I knew the guys at Lockheed Martin because I worked with some of them when I was there, and we would argue and fight and go on and on how we're going to navigate the Viking mission. And so in June of 1976, we land the thing on Mars, and I didn't know it, but Bill Melbourne wrote a paper on navigation of Viking. He had never been to a navigation meeting that I ever was aware of. But I kind of thought, when I first saw this paper, I thought, what? I said, I should have written that. It's scientific. But then when I read it, I realized what he had done. He had summarized all of the aspect of interplanetary orbit determination, which was the big deal when I first went to work there. How do you determine where the spacecraft is out there? And he came up with when you track with an antenna, you see the spacecraft rise and then it sets. And he came up with the when you determine the orbit, we get very very accurate orbit determination, and it was kind of hard to figure out how could this be so accurate, And what he came up with is what we call the Hamilton-Melbourne equation. So he did it with Hamilton, who was another guy that the two of them. When I first for years, if I was asked, what's the orbit determination accuracy if we send the spacecraft to this asteroid out there, and I'd say, how far away is it? And it's like 3 AU. That's 3 times the distance to the sun. That's 500 million kilometers. So I'd say, okay, our orbit determination, I multiply that times 0.5 microradians, 0.5 times 10 to the minus 6. 5. That's the angular measurement accuracy, and that's how accurate we could determine the orbit. Mm-hmm. So with the Hamilton-Melbourne equations, we can just about solve all the navigation problems that have to do with interplanetary. And what he discovered was, and he wrote this paper on it, which is a very interesting paper. I read it. Rare that I actually read a paper all the way through, get anything out of it. He determined that people, when they think of determining take the range, the range to the spacecraft. So people think that you can put an antenna in Australia and an antenna in California, and with the baseline between them, if you measure the angles, you can like a surveyor would do, you can determine how far away you are.
Mm-hmm.
You can't do that because the lines coming in, it's so far away that the lines are parallel with each other. So you cannot determine the orbit by the typical surveyor technique. It's the angle you want to get because you know how far it is. It's just in the light there, it goes there and it comes back, and you know how far it is because of the light round trip light time.
Mm-hmm.
It could be 40 minutes, 4 hours, it could be a long time. The moon, it's a tenth of a second. We're going quite a bit further away than the moon. Mm-hmm. We're talking about hours, an hour of the light time. But what he determined was that the Earth is rotating, and the signal wave is coming in, and you can by knowing when zenith occurs, or by watching the rotation of the Earth, you can make a velocity parallax measurement, not a position parallax, which is what people always think of, which doesn't do you any good. Velocity parallax, and this is very accurate because the time is so accurate. We can measure to a billionth of a second. But you can measure this time so accurately that you can, and also you know where the station locations are to a few meters. Now that when I first went, station location was always a big problem. 2 or 3 meters of station locations is a big error. And so anyhow, that's what he did, and he wrote this paper. And I another thing is he went into describing navigation historically. I think he could do it really well because he did it so many times. I think his paper had very little to do with Viking. It had to do with this problem. Like for example, how measuring time with clocks, which is what makes this work, is a similar. That's been a problem was around during the Middle Ages, or when the first sailors first started going out in the ocean. Longitude is the problem. You have to, when you sail, let's say you're in England and you sail west, and you quickly lose. You don't know what the longitude is. So the only way to determine longitude is if you have a clock and you can set it for, let's say, noon in London. The sun is up at noon, and then you sail west, and you wait until it's exactly noon. The sun is right overhead, and if your clock is 1 hour different in time, if the time is off by an hour, then you're 700 miles from London. That's how you determine longitude. And he's got this in the paper, and he got other arguments like that. Well, when he came up with this, this is why it's important from a scientific standpoint. This is very rare that anybody at JPL ever does anything that's important scientifically. When they would determine where the stars are in the sky, they would and the planets, how the planets are going. They had these photographic plates, big telescopes, optical telescopes, and they take a picture of the stars, and then they get in with a microscope and measure microscope or something, and measure very accurately where the stars are on there, and they could determine the angles to about 10 milliradians, 10 or 20 microradians.
Mm-hmm.
Okay, and so that enabled them to determine all the planets are. Okay, ephemeris they call them. Well, with the radio telescope, by doing this velocity parallax, you can measure it 100 times, at least 10 to 100 times more accurately. You can get 5 microradians, not 10, but 0.25. So we can measure anything out there in we can get a radio signal through. It's very high precision. So it, we at the stroke of a pen, basically, JPL took over for the whole world, determining where the planets were. Just by virtue of the fact that we had these radio antennas and a spacecraft to track. We had the spacecraft and the antenna. So that was, that was very. The scientists didn't believe we could do this accuracy. It took a couple of years for them to catch on that we could do it. Because we're going to having spacecraft over there and are not crashing. That's the only way you can get there. That's the only way you can prove anything. It has to be very dramatic because the scientists have closed minds. Because they're.
I'm speaking with James Miller, author of Planetary Spacecraft Navigation. You can find more information about the book on the Springer website. If you like this episode of Technology in Space so far, please subscribe and hit the like button. If you'd like more books and information on space history or the science, technology, and business of space, check out my YouTube channel, Spacewalks Money Talks, my podcast, Technology in Space, and my website, technologyandspace.com. If you're looking for military history and general history, including true crime, please check out my YouTube channel, War Scholar, my podcast, Military History Inside Out, and my webpage, warscholar.org or militaryhistorypodcast.com. If you're looking for fiction, including sci-fi, horror, fantasy, mysteries, thrillers, film history, gaming, and more, please check out my YouTube channel, Chris Alvarez Full Contact Nerd, my podcast, Full Contact Nerd Interviews, and my webpage, chrisalvarez.com or fullcontactnerd.com. Now back to the video.
But anyhow, I had done some work on molecules in a container. I wrote about 3 or 4 papers on this. And what I was trying to do is model a comet. And when the sun shines on the comet, it starts outgassing and gets the tail going, well, the molecules are flying off there, and they push it. They affect the spacecraft. They push on the spacecraft it's like a wind. So I decided that the way to do this is figure out how many molecules are coming off. What's the molecular weight? And so it's a kinetic theory of gases. So I was able to use that to figure out how much pressure is pushing on a spacecraft and how much the trajectory is going to be perturbed. I did that on Viking.
Okay.
So one day I decided, I wonder if I could put a bunch of molecules in a computer program in a box, maybe 100 or so, and let them bounce around in there, computing where they are, and see if I can duplicate Maxwell Boltzmann. They did this in they came up with the kinetic theory of gases, and that was Maxwell and Boltzmann. And distribution is a curve that goes up and then comes down like that. And that curve is well known in physics. I was seeing if I could generate it. Well, I didn't realize how fast the computer was. When I started working, I noticed that I could do 1 million molecules. And I stick them in a little box, and I was able to duplicate the Maxwell distribution with very high precision by doing 1 million molecules. Well, it turns out that it's unbelievable how fast the computer is. I can never imagine for each collision that a molecule makes. You have to search through all the other 999,999 molecules to find out which one you're going to hit next.
Yeah.
And then you have to repeat this. Well, I came up with some efficient ways of doing that, and I could simulate 1 million molecules for many collisions, and I could put all the molecules in there and just have them all at rest, and just have put one molecule in there and going at the speed of light. Basically, mathematics doesn't care about whether it's real or not. And then eventually, within a few collisions, it goes to the Maxwell distribution. So I thought that was neat. That kind of verified that I knew what I was doing with work on Viking and all that.
Hmm.
This was a time when I sort of didn't have anything to do, so I was just playing around. And I discovered that my distribution did not match the Maxwell-Boltzmann distribution. But I knew how to make it match. But then if I did it right, it would be off by about 5%. So I was able to show on a computer that the Maxwell distribution is not the correct distribution. And this is like saying that Einstein, Maxwell's famous. These guys are. And so I knew that I was going to have a hard time convincing the world that I actually had that distribution was incorrect. But I did find a couple of papers where people had actually tried to experimentally do this by putting gas and shooting it out and ionizing it, shooting it out into it, and measuring the velocity and counting the individual molecules. And in 1957, these two guys did this, and they come up with a curve, and the curve was a little bit off, and that was the amount that when I simulated it, I got that same thing. So it was off by the same amount. So I thought, oh, these guys are really gonna be excited. I'm gonna let them know that their experiment was correct. They were just using the wrong theory to verify it. They thought that their experiment was wrong or off a little, and they made a point about it. They were very honest. These guys were very honest. This guy, one of the guys that wrote the paper, got a Nobel Prize, and the other one was a graduate student of his. So I called up the physics department and I think it was one of those Ivy League schools. I forget which one. And see if these guys are still around. They're both dead.
Oh.
So I thought, okay, now I'm really. Those guys would have known what I was talking about right away, and I would have been on. That would have been it. Of course, they take my work and never mention that I ever. That's all right. I don't care. But now I realize I'm going to have a hard time selling this because I'm not going to. So I wrote a paper on it and I submitted it to the Journal of Letters, the big prestigious journal for the physics people. And they wrote back and pointed out that I didn't do this and I didn't do that, and therefore my results are not right. And I looked at it and I said, well, these guys obviously don't know what they're talking about.
They didn't understand the concept like you did.
I said, find somebody that really that has done simulations on a computer and have them read it and let me talk to them. I'm not interested in somebody that doesn't know how to run a computer. It doesn't even you can do this with a computer. So I decided, I was talking to Bill Melbourne at lunch. I do have in my story, I do have a little bit of a relationship with him. First of all, Hamilton Melbourne. I said, okay, look, I was more diplomatic in wording this because I didn't want to say something. I said, Hamilton Melbourne, you did these famous equations. I said, I don't believe that two people could do that. I think it had to be either you or Hamilton. Because teams never do anything creative or original. Everything that's creative and original comes from one person. But management doesn't like that. So what they'll do is they might manage to get this one person on a team, and then they credit the team, and then everybody's happy, So I've been playing that game for 35 years, so I knew what they were up to. So I asked him. He says, I did it. It was all mine. And he managed to convince me that he did do it. Hamilton. I think Hamilton may have been his boss at the time. I didn't realize that because he rose up higher than Hamilton. But they were both very obviously very friendly people each other, and so they didn't care one way or the other who gets credit for anything. JPL people can be very modest. The ones that really do something original are usually very modest. If you can talk to a really top scientist, you can they're very nice people. You can really make some headway with them if you can actually get them to listen to you. Anyhow, so I gave him, I explained my theory of molecule collisions. I said, I'm having trouble. He says, well, I said, what I find out is the only papers that scientists are interested in publishing are settled science. But in other words, real science, by my definition, is you come up with a theory and then you test it with experiment. And if you're a good scientist, half the time you're going to be wrong. If you're a bad scientist, you're just not challenging yourself very much.
Right.
If you're a student, you're not allowed to do anything. You're not allowed to question anything. Your science is geared toward confirming what we already know by doing an experiment to show here are the numbers for this situation. Here are the numbers, but they never challenge the theory. That because the theory is settled science. Well, I was challenging settled science. Well, they have a name for people that do this. They call them Einsteins. Because there are a lot of people who do general relativity, and they think that they know something better than Einstein, and they probably do. And they try to get a paper written on it, and the journals don't want to talk to them because it's settled. That's all settled science. We don't want to have anything to do with it. It's very hard to get new ideas, and unless you have an experiment that is very convincing. That's about working at JPL, because it's very convincing when you send a spacecraft out there and it doesn't crash into something.
Yeah.
So anyhow, I'm telling this. He says, guess what? He says, on the 100th anniversary of the Maxwell-Boltzmann discovery, the distribution, which I'm saying is wrong. He says, I did a study when I was at Caltech. And I read their papers to verify or to see what they had done. And Feynman was Richard Feynman. I don't know if you know who he is.
Sounds familiar.
Richard Feynman is the famous, he was on TV a lot. He was regarded as the smartest man in the whole world. He got a Nobel Prize for doing some quantum electrodynamics or something like that. But he was Feynman's student. Feynman is probably one of the best known professors at Caltech. And he said, I read the paper and I gave him my paper. I read your paper, and I think that Maxwell and Boltzmann are right. And I said, okay. I said, I'm not going to hold that against you because you're challenging, thinking that I'm wrong and you're right. Because you're wrong, I know that. But I'm not going to hold it against you because obviously I have respect for all the work you did, and I don't want to get you in any trouble. I sort of said something like that. But he helped me because he convinced me that I'll never get anybody to ever. The only way I could get anybody to verify that what I had done is correct is by having them write essentially the same computer program that I wrote. Mm-hmm. And this would take them a month, maybe, a couple of weeks. I'm fast because I've done a lot of this. Just to get them wound up on it, and it would take a long time. And so until somebody does that, my theory will never be accepted because I can't prove it other than by making computer runs. And scientists generally don't accept computer results as having any validity at all. I point out to them that all the work that I do on navigation is done with a computer. Mm-hmm. Equations, I don't care that much about the equations. The only thing I care about is my computer program.
And you've had success.
I was doing some work when I was on the NEAR mission. One of the things that really concerned me was we could determine where the orbit was, and then when we lowered it, we had to redetermine every time we lowered it. And the closer you got to the asteroid, the harder it was to determine the orbit. gravity. And so it got really difficult. And landmarks, instead of looking at big landmarks, every time you went down, you had to pick a bunch of little craters inside of the craters. And every time you look at the crater is like this, and then you go down closer, and then you're looking for craters inside the craters to use as landmarks, because the smaller the crater is, the more accurately you can locate it. It's big, you can't find the center that accurately. I have done all the studies to show that we can navigate and get into 25-kilometer orbit and all that, but I was never really sure. And the problem was that in order to make a prediction 10 days in the future, which is what we needed to have the time to get the data and get the maneuvers to put it back on track and all that, we needed a 10-day period of time to do that. It took about 5 days just to get the data. We had to wait for the data to come out. And so I had to be able to make predictions that were good to 100 meters 10 days in the future. And in order to do that, I had to know where I was at the present time to 1 meter. And I'm sitting there thinking for years, and we do 1 meter orbit determination. Are these results that I'm generating right or not? And I couldn't tell the management my concern, because I know that they would just either ignore it, or they would, if I was really convincing, then they'd get somebody else to come in and help me or something. It would become and we didn't have time for that. We're getting too close. And one of the smart guys that I was working, he's now a professor of head of the Department of Aerospace Engineering at Boulder, Colorado. But he was a young guy helping me. But he was very smart. And he comes to me one day and he said, "You know what, Jim?" He said, "In order to get that prediction to 100 meters out there in 10 days, you have to know the orbit within 1 kilometer or 1 meter." I thought to myself, "Oh, he figured it out." And I said, "Yeah, you're right." I said, "Are you sure you could do that?" And I said, "No, but we'll find out when we get there. If we can't, we're not going to go in a 25-kilometer orbit. That's going to be the problem right there. And there's going to be a lot of people that are going to really be mad about it. But I don't care, because I'm going to retire anyway, and I'm not worried about it." And he makes it proof. He says, "You have to prove it. You have to prove it. The mathematics are correct." I said, "Look, the only thing I have to do is 3 months from now is I have to have a computer program that's going to process the data, make the predictions, and enable us to do navigation. Whether the mathematics are correct or not, I could care less at this point. I am sure the mathematics are right, but if they're not, there's no way in the world that we're going to be able to fix the mathematics up. Find the mathematical error and fix it up in time to do the operations." Mm-hmm. I'm not even thinking about whether I'm not going to prove. I don't have to prove anything. Mm-hmm. But I'm wrong. Yeah. I got into it. The time for proof is 5 years before you propose the mission. That's when you prove it. After you proved it, then you just do it. The last thing in the world I want is to find an error in my program 2 days before we're going to do a maneuver. I don't want to find it. I'd rather.
Yeah.
Anyhow, that was my experience with Bill Melbourne.
Cool.
And I miss him, because I think he's the last of the really sharp guys, that did original work. One of the last of the really highly respected engineers that you ever lived.
Yeah. Well, it's sad he's gone, but at least he left a legacy, a pretty cool legacy. So
his wife, I had to be careful when I'm talking to him, because his wife could hear everything I say. I couldn't tell him how. You know that I don't like managers very much, because his wife. He still comes to the meetings, to the luncheons. She comes by herself. And she hears all this about him, because this paper has all of a sudden become a hot topic, because now that he's dead, we can talk about him. I always say, I said, I said, if you want to say something bad about somebody, wait until they die, then you can say it. So if they're alive, you have to say good things about them, because you know.
Yeah. Well, let's. Can we? Do you want to talk about Mariner now? Those issues you had brought up before.
All right. Uh, I was going to mention some. I was working in hardware at this time, and the Mariner was a big redesign. It was the first really big redesign of a spacecraft that brought it up to date. The original design of interplanetary spacecraft was the Ranger mission, and there were 6 of them, or 7 of them, and the Surveyor also was in the same time frame. But they only sent two or three spacecraft to the planets. So Mariner 6 was like, it was the 6th one, but a couple of them had failed. So this was like the 3rd time anybody had ever sent a spacecraft in the United States now to another planet. And now we had a spacecraft that's completely redesigned, and it included high-speed telecommunications, 100,000 bits per second. Some of the data that we would get back earlier was like 8 bits a second. It would just tell you where something was turned on or off. That's about all you could get. You could get some data, some numbers down once in a while, but the data rate was really slow. And this was high-speed block-coded data. Now, this is what the internet is. The only difference between our communication with the spacecraft and the internet was the internet takes the same transmission and does switching circuits, telephone switching circuits, so you can communicate with different people and switch data around. But and we also had a scan platform, a movable scan platform with all the instruments mounted on it, and we could point it with it. And we had a computer, first computer on a spacecraft. And I developed the software for the ground to control that computer, because I was the only one who knew how to program a computer, because engineers didn't program computers, because that's for programmers. The programmers are a lower form of life. Now we're a higher form of life than engineers, but the trouble is, if you think you're really at the top and really smart, be careful, because there's always somebody down below you that's going to overtake you. Once you get that attitude, they're going to make it their life duty to show you that they know more than you do.
Yeah.
So engineers who didn't like the program, they sort of got pushed aside. I knew that was going to be the case, because when I first started working at Westinghouse, I worked in I had an electrical engineering degree, and vacuum. Actually, on a nuclear submarines, they have what's known as a magnetic amplifier, and vacuum tubes, all radios and things like that were vacuum tubes. And even a car radio had little vacuum tubes in it. I had a portable radio that was with vacuum tubes, and the transistor had just been invented in 1948, and by 1955, that's when we started getting these Sony transistor radios. That was the first big production where they actually used a transistor. Okay? So there was a lot of new technology in the spacecraft, and one of the things that they was new was integrated circuits. The guy who invented, that's the chips, what a chip, the chip that you have that runs all your computers. A printed circuit, we call them. Before, that was all done on circuit boards that had discrete components, and now you could put 1 billion of these things on a little.
Yeah.
You just print them. You work out the circuit on a big thing like this, and then shrink it down and print it. That's what they do, and this was new. So printed circuits was a new thing on Mariner. Or the what did I just call it? Okay, anyhow, that kind of type of device. We're doing our testing, getting ready for launch, and we're making up simulated data, and this is going on and on. One of the things when you do something it's new for the first time. You have to practice it 100 times. I mean, we just do things practicing over and over because management wanted to make sure that we're not going to make a mistake, especially on Viking. It's $1 billion. That's a lot of money. I want for the price of that spacecraft, I could rebuild all the buildings in Los Angeles that I could see. What a spacecraft! If we crash it, it's like wiping out. It's like dropping a bomb on Los Angeles and destroying every building. That's $1 billion. That's like 10 billion today. Well, actually, now it's $1 billion. So yeah. But anyhow, we'd be sitting in operations, and one of the things that was happening is all of the systems, the telemetry, the telecommunications, the computers were failing because the integrated circuits were failing. So we're trying to figure out what to do because we're going to launch in a couple of weeks, and things are failing. So they sent a team to Motorola, I think it was in Phoenix. Mm-hmm. I'm saying Motorola. A lot of my memory isn't as good as it used to be. I'm bringing out a lot of stuff that's really old, so I might not get the right players or the right time. I'm doing the best I can. Okay. We sent this team to try to figure out what went wrong. Why are these failing? So they're looking at the assembly line, and they had everybody do exactly what they did, in order to try to figure it out. And this woman takes a rag and dips it in some solution and wipes off the integrated circuit. And they say, "What are you doing?" And they figure out that she put some acid of some kind on them, and that caused them to fail. And so then they figured out that they had watched. It's like watching the COVID-19 death rate. It was going up and then it was curving down and coming down. So they figured out that if this chemical reaction is probably, if it's going to kill the integrated circuits, it'll do it within a few weeks. And then after that, if they survive that, they're probably all right. We don't have to worry about it. So we can launch a spacecraft. That's one. So they just decided to launch it. Okay, now I'm sitting there about 3 or 4 days before launch, and the guy says, the spacecraft, they lost pressure on the Atlas. The Atlas missile is just a balloon filled with fuel. Mm-hmm. And if you take the fuel out, it's just gonna, with all the weight on there, it's just gonna collapse. So they lost pressure on the fuel tank, and the spacecraft went over and bounced off of the gantry. And then they restored pressure and it popped back up again. So they wondered, what are we going to do? Are we going to launch this thing? And there's no time to take it apart and figure out what to do. So another great management decision. The project manager on Mariner 6 was his name was Harrison Schurma. He's the one that got, after 5 straight failures of trying to send the spacecraft to the moon, coming in, the Ranger 6 was the first success. He was responsible for making Ranger 6 a big success. So he could make decisions, and he had a guy that was working for him, who was also pretty tough guy. Let's say I won't mention his name. I didn't like him that much, but I like Bud Schurma. He was a really interesting guy. He just said, "Let's go ahead and launch it. Forget about that." And so now, when you get down to the very end, there's all of a sudden the geniuses start to click into action. So they come to me and they said, "We're concerned about a proton storm. What if a proton storm comes from the sun? What's it going to do to the spacecraft?" I don't know what he's talking about. So I go, they say, "Okay, you got an action item to find out what the problem, what the solution to this problem is." So I go walking over, and I walk in the halls, you know, with the division that I worked, and I found the guys that designed all this stuff, you know. And I said, what about a proton storm? Oh yeah, proton storm. Don't worry about it. That's not going to cause anything. That's not a problem at all. So I talked to 3 or 4 of them, and they all said the same thing. And I thought back and said, okay, now I gotta write down a memo answering this question as to whether or not we have a concern here. So for the first time in my life, I decided I'm just going to lie. I'm going to say that I'm going to say it's my idea, or I'm going to have the answer. I'm not going to say that I talked to anybody. I wrote down, and I wrote a memo. The only time in my life I ever done this, I said, there's absolutely nothing to worry about. That's the guys that are telling me, you know. Of course, they're not, nobody's going to, they don't have to write it down. I said, proton storm can't cause any problem. We don't have to worry about the proton storm. And that was the end of that. I had many, many problems like that in the future.
Mm-hmm.
Years. I always worked very hard to make sure that I was prepared. If I couldn't answer a question, I never knew the answer to any of these questions, but I could quickly do something, my own analysis, determine whether or not there's a problem here.
Mm-hmm.
I never, again, had to, but managers do it all the time.
Mm-hmm.
They're told that in order to be the head of the team, you know, that navigates the spacecraft, you have to be very confident. You know, really, they're as confident as Trump. He knows the answer to every problem. That's what you have to be when you're a manager.
Mm-hmm.
And so every time on all the projects that I worked on, decisions were made based on what I regard as flimsy information.
Mm-hmm.
Give me a week or 2 to study it. Oh, we got to know right now, you know. Oh, yes, we got to know right now. Okay, this is the best information we got. Here's what we're going to do.
Mm-hmm.
Go into the studies. And then I come back. What's really, what the problem really is, and what the solution really should be.
Mm-hmm.
But change what they'd already decided. But then I analyze what is the effect of doing what they decided to do. And 9 times out of 10, it didn't make that much difference, or it didn't increase the risk of mission failure by that much. So I just said, just let it go. I decided that this is the price I have to pay to do the work I do. Otherwise, if I can get in early, like I did on the near mission, I got in really early, and I buttonholed the key personnel. And when they said what they could do, I told them, hell of I said, are you sure you can do this? I'm going to design the software to do it that way. I mean, you're right. If you're wrong, I know I'm never going to get them to write a memo saying that it's wrong, you know, fire me. But I always went after them and made numerous trips to get 5 to 6 laboratory, and every time there's just one guy. He claimed that he could, when you point, his attitude control system was so accurate, unbelievably accurate. That's accurate for pointing. APLs was 100 times, our spacecraft were 100 times worse than that. They said, look, if you can point that accurately, I don't have to have a star in the image with the crater. My plan was to images off to the edge, and you have the asteroid, and here's a crater, and here's a star, and we have to know the distance between the crater and the star. If he could look at the stars, determine the attitude, and tell me where the star was, and then I didn't have to do that. So I could get some good images by looking straight down, looking off the stereotype usually.
Mm-hmm.
It said the CCD, charge coupled device. That's a video camera. They're all your cameras are. This camera here is a CCD. That's pixels. They're like 1,000 by 1,000, and they're on a little chip. But maybe a little chip. Ours was 512 by something like that. He said, look, I could take a star and I could run it down between the pixels so that you'll never see the star. You won't hit a pixel light up. So I could point the spacecraft. I sort of, it sounded unbelievable to me, but the reason he told me he could do that was because he had done some Star Wars where they have to point spacecraft at missiles that are coming at them or something like that. They developed a spacecraft that could really work with very high precision. That was making this mission
So yeah, the purple plague. I'm still interested in that. I've mentioned it a couple times.
The purple plague was what was the stuff that they had on those integrated circuits. When she wiped it on, it was purple.
That was the purple.
And they noticed that the things were purple. The one failing had purple on them, so they called it purple plague.
And how about, you mentioned the scan platform unlatch? Maybe I misheard that.
Oh yeah, okay. Well, that involves that's what got me known enough that when I quit JPL, I came back. I quit for a year and a half and then came back. The one thing that I did which was on Mariner 6, that made me known amongst the management over there, that when I called up and said, hey, I need a job, they just hired me right away, because they knew like I said before in a previous one of these lectures, management would rather have somebody that they know can do the job rather than Einstein, who they'd have to train. Probably have a hard time getting him to do, because he would be bored. But if you find somebody that knows how to do something and are willing to do it. So but anyhow, the problem we had was that we launched the Mariner 6, and we were going to launch Mariner 7 a couple of weeks later. But about a week after launch, there's the scan platform, which was a thing that were all the instruments on, that it could rotate up and down and point. You keep the spacecraft still and you point the scan platform. It had to be unlatched, because during launch, there's a lot of vibration on a spacecraft during launch. That's what caused a lot of failures on the Ranger 6. The big failure that they were concerned about was the Vidicon shorted out because of the vibration. A relay, click shut, mechanical relay, and shorted off the TV camera. So they were the scan platform was latched down. So they have to unlatch it so that they can move it. Well, this is unbelievable. But the way they do it is they had, I can't remember the exact mechanism, but essentially what it amounted to is there was a spring that held the latch closed. And then they had a squib, which is a little explosive device that they use to break the thing, so that the spring would then move and unlatch the scan platform. And somehow hydrogen gas got involved in this. There was a little container of hydrogen gas that was used to maybe unlatch the scan platform. That's what it was. So what they would do is they'd fire the squib, and the hydrogen gas would then vent out and take the pressure off. But they were concerned about the gas escaping from the spacecraft perturbing the trajectory. So they vented it to a T, a T like this, and so it would go like that, and so there would be no net force at the T. So then they don't have to worry about the outgassing from the spacecraft, because it could cause the trajectory. Well, they unlatch the scan platform, and the spacecraft starts to turn away. Lost sunlock, lost Canopus track, and then the orbit determination guy said the spacecraft moved 1,000 kilometers at Mars. So they said something went wrong with this guy. It actually propelled the spacecraft. And I'm sitting there, I hear the story, and I said, and they told me, what happened, about the T and all that. And I said, I wondered if I could see it, nobody knew what was going on. So I went down to the Von Karman Auditorium, where all the news people come to cover the press. It's a big auditorium, and they have spacecrafts on display there. Well, they had what we called our proof test model spacecraft, and it was down there. It was the actual spacecraft. It could have been sent to Mars. It was an extra. See, we had built two, and then we had an extra. Money was a lot freer than it is now. Let me put it that way, because they don't do it anymore because of the money. You guys are stupid when it comes to money. If you don't know how to spend money by the bushel baskets full, you're not of any use in the space program. Let me put it that way. But anyhow, I went down there. I found the T, and I looked at it. And I said, "Oh, look at that! I know what happened. What happened was the T was in a big cavity that acted like a rocket engine. So when the gas came out of the T, the fact that it canceled out at the T, that didn't do anything. It expanded into this vacuum and moved out in a certain direction, just like a rocket engine. Well, from my kinetic theory of gases, I knew how many grams of hydrogen was in the container that did this. But I had one advantage. The trajectory people could see the trajectory move, but they had no idea about the attitude of the spacecraft. The attitude people could see that lost the attitude, but they couldn't figure out anything about the trajectory. So they need somebody that knows everything. And that's always me. If it's not me, I tell them that anyway. Because people who know everything know that they don't really know very much. People who think they really know a lot are people who know a lot about a little of something. Okay. Anyhow, what I figured out was that there was a certain amount of force, and I looked at the sun sensor, and there was a little parabolic arc in the data because it only goes about a degree or two before, maybe 3 or 4 degrees before the sun sensor loses the sun. It's a knife edge that the sun shines on a little detector. That's a JPL invention, by the way. A little knife edge, and the sun shines on it, and it tells you where the sun is. So I was able to determine for a few minutes what the attitude acceleration was, and then I took the trajectory miss of 1,000 kilometers, and I worked it back, and I figured out how much velocity it took to cause that much error, and what the direction was. So I figured it all out, and then I took that and applied it to Mariner 7, which was on its way. This is what would happen with Mariner 7, because it's going to do the same thing.
Right.
A different trajectory. It's going to be a different attitude. And I said, well, we're lucky on Mariner 7. It's because of the trajectory. It isn't going to be much of a perturbation at all. The trajectory won't perturb very much. And I was right. I was able to figure out what the problem was. Half the problem. Convincing somebody that you figured out what the problem is usually almost impossible. But if you can apply it to another spacecraft and then tell them what that's going to do, then they become believers.
Yeah.
And I had a little bit of fame there amongst one person who understood what I did, and he hired me back later on.
It's worth it. If he has the money, that's who you want to convince.
Yeah, right. He's a pretty high level guy now. I've worked with some people that are very important people. Like the guy that's the current director of JPL, I worked for him. And the guy that was my boss, the one that got me fired, basically, he became the deputy laboratory director. And when I came back, after I quit because they tried to fire me, and then they decided not to, and I said, "Hell yeah, I'm getting out of here." And a year later, I came back, and then every time I saw him in the hall, now he's a big manager. He's up on the 9th floor of building 180, and every time he'd see me, we'd stop and talk, I found out that the people that I fought with the most on Mariner 6, especially the programmers, we were lifelong friends after that because we both realized how dumb we were. How we're arguing about things that we knew nothing about, but you had to do something. And some decisions had to be made. And some people's attitudes, solutions to the problem were a little better than others, but basically we didn't really know what we were doing half the time. And so you make a lot of enemies that way. People can really get angry because when people have an idea that they think they know, they manage to convince themselves that they really know it. Mm. Try to tell them that you don't know it. This is what's really. Then they get really angry. One of the experiences that I regard as one of my best experiences working with doing that scan platform thing.
This ends part 1 of 2 parts. Thank you for watching this video version of Technology in Space. If you like the episode, please subscribe and hit the like button. If you'd like more books and information on space history or the science, technology, and business of space, check out my YouTube channel, Spacewalks Money Talks, my podcast, Technology in Space, and my website, technologyinspace.com. If you're looking for military history and general history, including true crime, please check out my YouTube channel, War Scholar, my podcast, Military History Inside Out, and my webpage, warscholar.org or militaryhistorypodcast.com. If you're looking for fiction, including sci-fi, horror, fantasy, mysteries, thrillers, film history, gaming, and more, please check out my YouTube channel, Chris Alvarez Full Contact Nerd, my podcast, Full Contact Nerd Interviews, and my webpage, chrisalvarez.com or fullcontactnerd.com. Thank you for watching.